Welcome to the next video in the Measure Theoretic Probability series. This is video number 8. We'll be discussing sigma algebras. So, a sigma algebra is extremely similar to an algebra. In fact, a sigma algebra is an algebra with just one more requirement added on to the collection of properties that we require. And that property is that in order to be a sigma algebra, it must be closed under countable unions, not mere pairwise unions, but countable unions. So what that means is that if you have any collection of elements of this subset of the power set, call them E1, E2, and so on, all of them elements of S. By the way, notice I used a calligraphic A to denote a mere algebra, whereas I use this calligraphic S to denote a sigma algebra. I'll try to be fairly consistent about using it that way. On that theme, I might as well go ahead and mention that I'll also be using E's for measurable subsets. That is to say, E's for elements of sigma algebras and algebras. I'll be using A's whenever I want to denote some subset of omega that may not be in the sigma algebra. That is to say, I'll be using the letter A when it's an arbitrary subset of omega. This is exactly the opposite of the convention used by the textbook. I'm only doing it my way because that's what I'm used to. That's how we did it in the classes that I took and in some of the other textbooks that I've read. So I'm not sure why Ithrea and Lahiri have switched the notation. I'm sure there's some reason for it, but I'm used to doing it the opposite. So I'll be persisting in that. But anyway, so we take E1, E2, and so on to be elements of S. Then to be closed under countable union, we must have, whenever that is the case, the union over them is also in S. That's that extra condition tacked on to being an algebra is what it is to be a sigma algebra. Why do we have sigma algebras beyond just algebras? Well, thinking back to the history that we talked about with Lebesgue integration, we know that the pre-images of certain functions may be countable unions of intervals, for instance, and we sure hope that we can handle that case because it in fact does come up. And so we know that we need to handle it for length measure, and in lots of other measures, we'll also sure hope that we can handle it. So we make it right. So we define it because it will be an interesting and valuable property for some important applications that we have. By the way, notice that there's no distinction between pairwise and countable unions if you only have a finite collection of things to take unions of. So in particular, if omega is finite, then sigma algebras and regular algebras are just the same thing. By the way, also notice that the maximal and minimal algebras are also maximal and minimal sigma algebras. So in both examples, you can demonstrate closure under countable unions. Okay. Now, I have defined a sigma algebra slightly differently than how the textbook does. So I want to prove a theorem that will, in fact, make it clear that it doesn't matter if you define it my way or the textbook's way of defining it, they amount to the same thing. So here's the claim that I'm going to prove. If you take any subset of the power set that contains the universe and is closed under complements and is closed under countable unions, then that collection is automatically closed also under pairwise unions. And therefore, the collection is an algebra, and therefore the collection is a sigma algebra. And notice that this collection of properties in the claim, right, in the assumption of the claim, is exactly how the textbook defines a sigma algebra. So I'm showing you that whenever you have something that satisfies the requirements given in the textbook, you actually have something that satisfies my requirements. And the converse is even easier. So anyway, let's prove this. And the way to prove it, right? We're trying to prove that closure under pairwise unions holds. So we're going to take a set E1 and a set E2 and try to argue that their union, right, these being in S, we want to prove that their union is also in S. And we need to use the fact that we know that this is closed under countable unions. So we need to come up with some countable sequence of sets, which is equivalent to just this pair, right? Taking a union over the countable sequence of sets is equal to this union of this pair. And so what we would love to be able to do is to make the first set in the sequence just equal to E1, the second set in the sequence equal to just E2, and take everything else after that to be the empty set. But in order to do that, we'll need to know that the empty set is in our sigma algebra. And although it follows very easily, we should go ahead and mention why we know this. So because omega is in S by assumption, its complement is the empty set, and that is in S because of closure under complement. So there you have it. Now everything that I've described about how we're going to implement the rest of the proof follows immediately, and we're done.